morning, fellow humanists. It's a pleasure to join you on this cool and sunny Sunday. My name is Todd Kimball. It's an honor to be your MC. Welcome to fellow HGP members and those around the world watching us on YouTube. We have an exciting topic today. I know you're going to enjoy it, so I will keep my remarks to an absolute minimum. A reminder that humanism is a rational philosophy informed by science, motivated by compassion. It advocates the extension of participatory democracy and the expansion of an open society standing for human rights and social justice. One of my favorite readers joins us this morning. He is especially talented when we have scientific topics. I welcome as our reader this morning, Mr. Laurent Beauregard.
The reading this morning is taken from a book by Stephen Strogatz. The title of the book is Infinite Powers and goes like this. It's a curiosity of history that the world was changed forever by a branch of mathematics known as calculus. How could this be? The answer lies in a quip that physicist Richard Feynman made to the novelist Herman Wouk. Wouk was working on a book about World War II. He went to Caltech to interview Feynman, who had been involved in developing the atomic bomb. After the interview, Feynman asked Wouk if he knew calculus. No, he admitted, he did not. Then you had better learn it, said Feynman. It's the language that God talks. For reasons nobody understands, the universe is deeply mathematical. Maybe God made it that way. Or maybe it's the only way a universe with us in it could be. Or maybe it's because non-mathematical universes cannot harbor life intelligent enough to ask the question. In any case, it's a mysterious and marvelous fact that our universe obeys laws of nature that always turn out to be expressible in the language of calculus. Certain sentences known as differential equations. These equations describe the difference between something right now and the same thing an instant later, or between something right here and the very same thing close by. There seems to be something like an order to the universe, a code, an operating system that animates everything from moment to moment and from place to place. Calculus taps into this order and expresses it. Isaac Newton was the first to glimpse the secret of the universe. He found that the orbits of the planets, the rhythm of the tides, the trajectories of cannonballs could all be described, explained, and predicted by a small set of differential equations. Today, we call them Newton's laws of motion and Newton's law of gravity. Ever since Newton, we have found that the same pattern holds whenever we uncover a new part of the universe. Everything bends to the rule of differential equations. I believe that this is what Feynman meant when he said that calculus is the language of God. If anything deserves to be called the secret of the universe, it is calculus. The universe is mathematical at its very core.
Thank you, Laurent, for a thoughtful and timely reading this morning. Thoroughly enjoyed that. And now I am very excited to welcome our speaker. But first, a brief introduction. Humanists want the truth. Humanists can handle the truth. It's refreshing when you have an expert on a topic to point out where movies take liberties with accuracy. We have that opportunity this morning with our presenter, Stephen Kral. The film Oppenheimer shows stylized scenes of people hard at work. This talk addresses the problems that participants in the Manhattan Project dealt with. Kral earned his Ph.D. in physics at the University of Minnesota. He was recognized with an outstanding physics teaching award at the University of Utah. In addition to physics, he has also taught interdisciplinary studies in history and the philosophy of science. Let's have a rousing ovation from those at the Friendly House and a warm yet muted welcome from our Zoom audience for Dr. Steve Kral.
Well, good morning. I'd like to give a little brief introduction to how this came about. When the movie Oppenheimer was shown, after the movie, in Early Birds, Carl Levin came in one day and we talked about the movie, and he said, one thing I'd like to know is what those guys were doing there. And I thought that was an interesting question. And I said, well, why don't I give it a try to explain what was going on, what those guys were doing in the movie. So when I began to look into this issue about what they were doing, I was reminded of something that occurred when I was a graduate student. And being a graduate student, I spent a lot of time in the lab. I was married, and my wife's mother would often visit my home, and she would find that I was in the lab, and she would ask plaintively, "What does he do over there?" And I remember trying to tell her what I did over there, not very successfully. So I hope that isn't what happens here. The Los Alamos primer, which you see on the screen, is a document that was put together after a meeting that took place in 1942 with Oppenheimer and a collection of physicists who met to discuss the problems that they confronted in trying to build an atom bomb. It was, of course, a very highly classified device and document. And as you can see, this is the front page of it, and it's been unclassified. By the way, if you have any friends who have classified documents at home, you might point this out to them that they should have it done. But this is the way the document looks. It's the Los Alamos primer. And what I intended to do when I first started planning this talk was to take the key elements of the primer and kind of explicate, to try to show you the details of what had to be done in order to ensure that the bomb would work and work well. And so when I looked at it, I looked at the sections of the primer, and what I see, it's a 22-section document. It begins with this object, what the statement of purpose of this project were, and a whole collection of topics that were going to be discussed and explored. Energy of fission process, fast neutron chain reaction, Newton spectrum, effective timbre on efficiency, et cetera, et cetera. And I began to look into more detail behind each of those. And what I realized is that what the physicists were confronted with and what they described in this document were questions that required a very detailed analysis of how a bomb works. And in order to understand why these issues are important, you have to know a great deal about what this particular bomb, how it would come together. And the deeper I got into it, the more I realized that to do what I was trying to do would be a very, very technical presentation. And I don't expect the audience to have the kind of deep understanding of fission bombs that would be required to make that useful. As an example, a key topic of this device is called the efficiency. The efficiency of the bomb is basically based on the fact that a bomb has so many pounds, if you like, kilograms, or whatever you want to use, of materials that can explode. The efficiency is the actual number of material that is exploded. So, and the ratio of those two is the efficiency. So, for example, if you had a 20-pound bomb and you set it off and 19 pounds exploded and 1 pound was left, you would have a 95% efficiency bomb. So, and when I started to read about this project, I realized that one of the first things I read was that the original design expected an efficiency of 1%, which is not a very useful bomb. And so to get from 1% to something that is more useful, that, by the way, they got to something like 19%, requires just detail after detail of detail attention. And I thought that may not be the best way for us to go with this. And I thought, well, what can I talk about? And I thought I'd show you a page or two of what the report looks like, because it has some interesting things in the introduction. The first section is object. The object of the project is to produce a practical military weapon in the form of a bomb, et cetera, et cetera, et cetera. By the way, while the description called the bomb appears in this document, Oppenheimer did not like people talking about the bomb, and I think the nickname they chose for this device was Gadget at Los Alamos. The second, as you can see, the energy of the fission process consists of a lot of numbers, and I don't think that would be a very productive presentation for us today. So what I looked at the list of things, and I saw some questions that I might have. What is a fast fusion chain reaction? What's nuclear fission? How did physicists develop the concepts that together make possible imagining such a bomb? What did the Los Alamos physicists know? How did they come to know what they know? And this is a very modest attempt to begin thinking about such questions. What I'm going to do is tell you how physicists came to understand what an atom is, what are the constituents of an atom, and how those constituents might come together in such a way to produce a bomb. So I'm going to talk about what needed to be known before the idea of a bomb could be approached. So I'm giving you a little bit of history about the development of physics. And as always, start in the beginning. The Greek atomists developed a systematic approach to the question of everything in the universe, claiming that they could be described as being made of indivisible bodies. These atoms were indivisible bodies. They strike against each other, rebound, interlock, or whatever the case may be. But at the base of all reality are objects that cannot be divided and whose interaction put in such a way produces everything that we see. In contrast to that particular view, the atomists, we have the Stoics, who believe the cosmos was filled with an all-pervasive substratum called pneuma, within which everything happens. It turns out, as I talk through this, you're going to see an example of something that might be called a pneuma, and many things that are called atoms. So the Greeks came forward with this concept, and the idea kind of hung around for a couple of thousand years without there being a great deal of progress made in understanding what stuff is made of. The four elements that I'm giving you here were elements that were produced by John Dalton in 1804, which is probably close to 2,000 years from the Greeks' original conceptualization. And as you see, the first element of Dalton's description, elements consist of indivisible small particles, and he called them atoms. I won't go on from there, but just to show that after 2,000 years of effort, there wasn't much difference in the understanding of what nature is really about. The real question and real difficulty that everyone faced was that you can't see, like atoms could not be seen. And somehow, in order to explore atoms, to see if atoms have structure, you have to somehow find a method to perceive them. And with this, I want to give you a brief introduction to what will be the center of virtually everything I talk about today, which is the electrical and magnetic phenomena. Now, this, we all know, we all go to school where a teacher came in with a glass rod and a silk stick and stroked the rod and was able to make your hair stand on your head and do that kind of thing. People came in with magnets that would basically allow them to say what the direction of north is. That there was a great deal of interest in these kinds of phenomena, which we call the electric and magnetic phenomena. And over time, people began to develop techniques where they could take advantage of such things. Volta in 1799 built a battery, called it a voltaic pile, compass needles were used. In the 19th century, physicists named James Clerk Maxwell developed a theory which we call classical electricity and magnetism. And in that theory, he described how electrical and magnetic phenomena can be used to sense and measure and control things that are electrical in nature. And you're going to see that at the center of all of the work done to understand atomic structure were electrical and magnetic measurements of the constituents of the atom. I'm not going to go into avoid going deeply into electricity and magnetism, but I do want to give you some sense about what electrical and magnetic effects, how they're actually, how they can actually be manipulated in the laboratory. And I want to talk about electrical effects. And one of the kinds of pictures, one of the things I'll be talking about today is the fact that if I have a charged particle, that green device with the little minus sign in it is intended to be a negatively charged particle. If I have a charged particle and I shoot it into a region between two plates that are connected to a battery, that charged particle will feel an electrical force. And that electrical force will divert the trajectory of the charged particle. In this case, it indicates that with that light-colored line, the particle moves down into the and collides with the lower plate. Putting charged particles between plates, you'll see happens again and again and again in this work. The second kind of effect I want to talk about is magnetic effect. And again, a magnetic effect for a charged particle to experience a magnetic effect, it must be moving. And that is illustrated here by the arrows with points on them. And if you shoot a charged particle into a region with a magnetic field, the charged particle will, the path of the charged particle will bend depending upon whether the charged particle is positive or negative. And that's illustrated here with the blue and red arrows. But an interesting and clever phenomenon, which is an important one in what we're going to be talking about, is if you have particles moving in both fields. If you can arrange a particle so to move in such a way that the electrical force acts on it to move it in one direction, in this case, I'm showing an electrical force to move the particle up, and the magnetic force moves in the opposite direction, those forces will cancel themselves out, and the particle will just move on a straight line. Now, that's a curiosity, except for the fact that because the magnetic force depends upon how fast the particle is moving, it's only at a particular velocity that the particle will move in a straight line between it. So this is a device that allows you to tell how fast the particle is moving. And we'll find out that that's an important feature as well in trying to describe the constituents of an atom. So what I want you to know is that I'm going to be talking about electric deflections in electric fields, deflections in magnetic fields, and these are called velocity filters. A velocity filter. That's all you really need to know, and recognize that what's required for those things to occur is that a particle be charged and that the electric and magnetic fields be present. If you're not careful in balancing the forces on the charged particle, it'll move off in very interesting directions. And so it's only at a particular balance point that that velocity filter works. Here's a picture of a real-world experiment showing charged particles moving in a magnetic field, and you can see all the curved lines and what have you. That's evidence that the world knows how to behave. So the first experiment that I want to talk about is work done by an English physicist named J.J. Thomson. And J.J. Thomson was given a Nobel Prize for his work on the discovery of the electron. And I want to give you a little bit of introduction to what he says. This is the lecture that he gave for his Nobel Prize. In this lecture, I wish to give an account of some investigations which have led to the conclusion that the carriers of negative electricity are bodies, which I have called corpuscles, which having a mass very much smaller than that of the atom of any known element and are of the same character from whatever source the negative electricity may be derived. In other words, there are things that he calls corpuscles, negative corpuscles. We call them electrons now. There are these negatively charged corpuscles. How does he know they're charged? Because if he passes them through that electric phenomenon, they'll be deflected. How much will they be deflected? It depends upon the amount of charge. He says these particles have masses very much smaller than the atom of any known element. So suddenly we have claimed that Thomson has seen elements of the world that are smaller even than atoms. Suddenly the fact that atoms exist and their indivisibility is being challenged by this study. And Thomson finishes his lecture with a very simple statement that the atom is not the ultimate limit of a subdivision of matter. We may go further and get to the corpuscle. So this is probably the first evidence directly that there is in the world elements that are smaller than atoms that can be identified, separated out, and studied. And a key point here is that they're all the same. How did he come to say that? Or excuse me, how can you discover a particle so small that nobody has ever seen one? Well, there's a device called a cathode ray tube. By the way, all of you had old TVs, black and white TVs with those big tubes. Those were cathode ray tubes. And the cathode ray tube was developed in the late part of the 17th century, 18th century, and people studied the gases trapped in a cathode ray tube, and under the influence of the electrical phenomena produced when you tie a battery. And what happens with this kind of device, and what is that you can discover that there are glowing gases in the cathode ray tube. And in particular, this particular illustration was intended by Thomson to make the point that whatever going on in these cathode ray tubes, whatever's going on, the motion of charges that occur in these tubes goes in straight lines. And you can see the straight lines in this tube on the right. The fact that you can cast a shadow by placing an object in the path of these devices is evidence that they're moving in a straight line. So first, J.J. Thomson demonstrated that these things move in straight lines. By the way, there was an argument between the British physicists and the Germans. The Germans didn't believe that the cathode ray particles, these corpuscles, were negative particles. They believed they were waves. J.J. Thomson presented this as evidence that they were, in fact, particles. They're negative charges. They pass. They're deflected in the fields in the cathode ray tube, and by deflecting them, people can measure the amount of charge and the mass of the devices. They have magnetic deflection of cathode rays. They're deflected, and deflection is the way you'd expect with a negative charge. And if you happen to direct the cathode ray in the same direction as the magnetic field, you don't get any of that deflection that we saw. The interesting thing was that by looking at the using a velocity filter, J.J. Thomson discovered that the particles in the cathode ray tube were moving at something like 1/3 the speed of light. These are measurements being in the 1890s, and he says that this speed is much greater than the velocity of any other moving body with which we are acquainted. Finally, by measuring the amount of deflection in an electric field, they discovered that the mass of these corpuscles, these electrons, was about 1/1700, the mass of the hydrogen atom. So it's a very, very tiny mass. And these are simply drawings to illustrate what I was talking about. If you have a cathode ray tube and you inject an electron into it, and there are metal charged plates, the electric charge is deflected, and by measuring the amount of deflection, you can determine the properties of the cathode ray. If you have another cathode ray tube, a lot of glass blowers in these laboratories, with both magnets and electrically charged plates, you can get deflections that are more complex by adjusting these devices, and by adjusting the strength of these magnets and electric field, you can make it such that the charged particles will pass straight through, and that'll give you an opportunity to measure the speed with which those are moving. So by making these measurements, Thomson presented the existence of something that was smaller than atoms, that had predictable properties, that could be measured and could be used. And that was the first example of scientists exploring what's within an atom. The second opportunity that came along to do such a thing was the discovery of radioactivity. Radioactivity was actually discovered by French physicist Becquerel. He had a uranium compound that was discovered to have a property of luminescence. And luminescence is a property where if you place a properly structured material in sun, the material will absorb energy from the sunlight. And if you take it into a dark room, the material will glow in the dark and re-emit, if you like, the energy that was absorbed from the sun. That's called luminescence. And it was something that was of great interest in the 1890s. And he was hoping to learn something about how this solar energy is stored. Well, he was preparing a sample of this uranium to expose to the sun so that he could get a measured exposure and use that measured exposure as a way of relating to the behavior of the luminescent device when it discharged the energy. And it turned out to be a very gray day in Paris. So he took his material that he had all prepared to expose, and he wrapped it in black paper so that the material would be protected from inadvertent exposure to light. And he took this black wrapped paper uranium, put it in the desk drawer, and went away because it wasn't a good day to make measurements. And as life happens, it turned out he wasn't able to get back to it for several days. When he did get back, he realized that he put this uranium wrapped paper on top of a photographic plate, and he was wondering if in fact he had done damage to the photographic plate by doing that. And he developed the photographic plate and looked at it, and he saw that the image of the uranium had in fact exposed the photographic plate in such a way that you could see the shape of the uranium that had been on top of the plate, but it had been wrapped up in black paper, so it certainly couldn't have been the luminescent effect that he was exploring. And he said, "Where did this come from? Where did this come from?" Well, after some exploration by others as well as Becquerel, what they discovered was that uranium, for unknown reasons, was emitting radiations, and that these radiations had a particular effect. They were capable of ionizing the air. Now, ionizing the air is a term that refers to the fact that a term that probably comes out of well, that if you expose air to a very large electric field, you can in fact change the nature of the air in such a way that it's charged. And it becomes charged through the process of stripping electrons out of the atoms, the electrons that J. Thomson has discovered. Well, this radioactivity was first discovered in uranium, and over the next 7 or 8 years, the radium was found in many other compounds, and in particular in materials such as polonium, radium. There was a gas called radon, which is a automatic, which is a gas that comes in the process of radioactive materials evolving. So there are two questions in it that one comes when one sees these. What are the radiations, and how is the radioactive emitter changed? I'm sure there are other questions you might ask, but that's the one that I'm addressing here. It turned out that the study of these emissions from uranium discovered there were 3 types of radiation. The first was a radiation which was called, simply because it was the first, an alpha radiation. They're least penetrating and most ionizing. That is, the alpha radiation emerging from the uranium doesn't travel very far. It can be easily stopped. They discover this by having a setup where you have uranium between 2 plates. Remember, we talked about the electrical plates, and the particles would be emitted from the uranium, and it could in fact discharge these plates. The fact that this material can discharge the plates is evidence that it's charged. So alpha radiations, for whatever reason, were caused the most ionization but least penetrating. Beta radiation is most penetrating and least ionizing, and gamma radiation behaves like X-ray. So very quickly, scientists realized that beta radiation, electrons, are part of the radiation process. They knew what electrons were, beta radiation, because J.J. Thomson had in fact done a complete study on them. Gamma radiation was very much like X-rays. They behave like X-rays, and they too had been studied when Röntgen discovered X-rays. Alpha radiation, on the other hand, was something that was not very familiar. I want to show you something. This is a drawing that comes from Rutherford's speech at the Nobel Prize, and it has up here a peculiar symbol. When I saw that, I thought, well, that's some particular kind of electronic device, not one that I'd seen before. So I went out looking for it, and what I discovered that it's one of a class of devices called an electrometer. And this is a nice picture because it shows 3 different kinds of electrometers, but the first one is the one that's most revealing. These are 2 gold leafs that are attached to a connection that you can make, a metal connection that you can make from the outside. And if you put a battery between this point and this point, you would charge these gold leaves and they would spread out. Like charges repel, and the gold leaves would spread out. And the purpose of the electrometer is to measure the quantity of electrical effect, and that can be measured by the amount of spread that these gold leaves experience. And these are similar devices, but not so intuitively obvious. One of them is a spring, and these are 2 plates, and if these plates acquire different charges, this plate will twist and turn, and there'll be a meter. You can measure how far the tip of this arrow moves. This is the device similar. The people studying radioactivity. This is a device that's a little more complicated. It's a little more sensitive, but all of them are based on the fact that if you charge different parts of the device differently, then forces will come into play to twist and give you a way to measure things. So as I said, beta radiations are electrons. They have small mass. Less ionizing suggests relatively less charge relative to the alpha particles, which are more ionizing. So there's a whole collection of data about the alpha radiation that was discovered as people studied it coming off of these materials, particularly the uranium. Alpha radiation was shown to be positively charged by these deflection measurements in both electric and magnetic fields. The deflection was very small compared to cathode rays, and that's an indication that the alpha particles are probably much more massive than cathode rays. The speed measured of these particles was very fast, 1/12 the speed of light. The ratio of mass to charge, which can be measured for these devices, was found to be similar to that of a hydrogen atom. As it turned out later on that by careful analysis of the alpha radiation, they discovered that it was in fact a material that was the nucleus of a helium atom. That is to say, it had 2 positive units of charge and 4 mass units in the device. Another interesting phenomenon here, and one that's very important in terms of using of experimenting with these devices, it was discovered that you could detect alpha radiation using an electronic counter. The Geiger counter was invented in order to detect alpha radiation. At the same time, another method was discovered, and that is that these alpha particles, if they struck a screen that contained a material like zinc sulfide, the screen would momentarily glow. It'd be a scintillation, there'd be a light flash. And that light flash was directly related to the collision of the alpha particle with the screen. So you could see the presence of alpha particles by watching the scintillation on a screen. So the question that I asked earlier, how can you investigate something that you can't see? Well, the invention of these devices that allow you to see or measure alpha particles was a path into seeing, in fact, how these particles show you themselves through these effects. These alpha particles were studied primarily in radiation from radium and its decay products. And I want to give you some numbers here because it's shocking how much energy is involved in these particles. For example, a kilogram of radon. Radon is a radioactive gas that is emitted by radium. Emits energy at a rate of 14,000 horsepower. And over the lifetime of this kilogram of radon, emit an amount of energy expended by an 80,000 horsepower source in one day. I use these numbers horsepower because those are numbers that are pretty common in English-speaking countries to measure energy and power. The rate of emission of particles from a 1 gram radium source in 1 second is about 62 billion particles. So from this radium source, you get a huge number of alpha particles that can cause scintillation on screens and that are quite energetic. That is to say, you have particles that are energetic, that can be detected, and that are charged. That's an important tool for the experimentalist. The discovery of electrons led to a greater interest into the structure of atoms, the characteristics that people talked about for these atoms is that electrons are negatively charged and are constituents of all atoms and are the source of spectral radiation, that is light. Matter is ordinarily neutral. In order for matter to be neutral and for negatively charged electrons to be in them, there must be some positively charged constituent in all atoms to cancel out the charge of the electron. Electrons are very small mass, and most atomic masses must be associated consequently with the positive charges. And finally, atoms not radiating energy must be static without charged particles acceleration. That simply states the fact that the only way radiation light can occur is if a charged particle is accelerated. Since atoms do not radiate light ordinarily, they must have no electrons or charges within them that are being accelerated. After the discovery of the electron, and with the characteristics of the atom that I just described, that atoms must have both negative and positive charges that are embedded in them, J.J. Thomson, the physicist who discovered the electron, proposed a model for atoms. He was a Brit, and he called this model the plum pudding model. And what very quick description of it is, it's a ball of positive charge about the size of an atom, and embedded in that ball of positive charge are enough negative charges, electrons, so that the net charge of the positive charge and electrons is zero. So this is a model of the atom. This is the first model of the atom. This is a model of the atom that includes details of the interior of atomic structure. The important thing about this is that if you could have shoot charged particles at a Thomson model atom, if for example consider the one that goes through the middle. Let's say that you're shooting a positively charged particle. Well, this particle traversing would not have much deflection because there's as much stuff above it trying to say push it that way. All of the forces on it are such that they're distributed, so there isn't much movement, much bending of the path of these particles passing through the atom. Well, Rutherford thought about this issue, and he realized that he had in these alpha particles a tool to explore the interior structure of atoms. If the atom looked like this, these black arrows would be the path of alpha particles passing through the atom. And he didn't expect that there would be a great deal of deflection passing through an atom that was put together according to the Thomson model. Well, Rutherford built an experiment in which he used a source of radium, which had a source of alpha particles. He shot the alpha particles directly at a gold foil, and he looked in a region beyond the gold foil, expecting that as the alpha particles traversed through the foil, they would be bent according to the degree with which they came into contact with other charges that exert forces on them. And as I say, he was with the Thomson model in mind. He didn't expect to see very much spreading of this beam, and in fact, he didn't. So, the first results, little deflection in the forward direction, and he thought this supported the plum pudding model. On the other hand, he realized that to complete the experiment, he should look in all directions, and he assigned the investigation of what's called backscattering, that is scattering back off of this foil, this gold foil, to see if that's possible. He didn't expect that because there was nothing in the Thomson model of the atom that was big enough to cause something like a alpha particle to bounce back. Well, so he assigned this backscattering as a student, and I can imagine what the student experienced, because the story is that he set up the experiment so that the alpha particles were striking, in this case, a gold foil, and he had a little detector, his eye, or a zinc sulfide screen, and he would look at the zinc sulfide screen. He set the experiment up. He opened up and set the collimator in such a way that the alpha particles bounced off the gold screen, and almost immediately he began seeing scintillation flashes on the scintillation screen. So, what was happening was that these alpha particles were bouncing off of gold atoms in the gold foil and being reflected back toward where they came from. The student called Rutherford, and Rutherford came down and looked at this, and this is the quote that he made when he saw that. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." This was a stunning result. To give you an idea of, we had a little talk today about mathematics is the base of our knowledge of physics. Just what happens in a situation like this is that Rutherford, in this case, did an analysis of a mathematical analysis of what would happen when you shot a gold at a gold foil. You shot particles that were positively charged, and you get to go through a rather long mathematical analysis, which I'm not going to go through, but that mathematical analysis suggested that in fact what was going on in this atom was that the positive charge of the atom is not spread out across the whole atom as Thomson had proposed, but it's concentrated into a very small volume. The scattering of these alpha particles that banged into it require that the mass of the atom be contained in that very small radius. And an analysis of this data, based on the kinds of mathematics that Rutherford was doing, suggested that the nuclear radius was not greater than about 10 to the minus 12 centimeters. It's a very small number. The atom itself is about 10,000 times the size of the nucleus. So an atom, by this, as a result of this experiment, is revisualized into something that has a very tiny, massive core at its center. The remainder of the atom, which surrounds the center, is 10,000 times bigger than the center. And as a consequence, the atom is mostly empty, free of matter. Now, this is a picture of what this nucleus would look like. This is the atom that Rutherford feels that his experiment justified. One point that you want to make about this, and this is a point that I briefly passed over earlier, that if you have a device, an atom that looks like this, you would expect that the electrons that surround the nucleus would be in motion. But on the other hand, if the electrons are in motion, the laws of electricity and magnetism require that those electrons radiate light. But that is not what happens. If that were the case, then everything you see, which has atoms in it, would be glowing with radiated light from the atoms. So there's something fundamentally at odds between those two phenomena. I'm going to go on and talk about the what other particles are observed. We now know that we've observed electrons. We know that positive charges are at the center. But what are the what is the shape of those particles that are in the atom and in the nucleus? And again, what Rutherford did in his studies was to take advantage of the fact that he has available this probe, which is a alpha particle, which he can shoot at nuclei and use it as a way to probe what the nucleus was like. So what Rutherford decided to do was to begin bouncing alpha particles off the nuclei of many other objects, and he was looking at objects that are lightweight, and began by looking at gases. And this is the kind of experimental device that he used. He would mount a source of alpha particles on this device, on this post, which could be slid back and forth. He would view on the left, you see this M, that was a that was a microscope that will allow him to look for scintillations on the screen that would occur when charged particles struck the screen. And he would fill this tank up with gases at very low pressure. What he discovered is that when he shot at nitrogen, which is a gas that's in the air, with an alpha particle, that the nucleus would absorb an alpha particle. And after that absorption took place, he discovered that this nitrogen nucleus would, in fact, absorb the alpha particle into the nucleus, and in a short time, the nucleus would disintegrate into the emission of an oxygen atom and a hydrogen nucleus. And this was the first known instance of a nuclear reaction. I could go back and explain, well, how did he know it was an oxygen atom? How did he know it was hydrogen nucleus? Remember, charged particles, you can use devices that are electrical and magnetic to determine their properties. And in addition, he had a zinc sulfide screen to determine their presence. They're developed a notation for identifying materials. Here we have a notation. The HE stands for helium. The upper left-handed superscript is how many particles are in the helium. The bottom subscript is how many positive charges are in the nucleus. So this is a way of describing an atom of helium. It has a nucleus with positive charges and electrons surrounding it. The experiment that Rutherford did in order to discover the proton, which is the nucleus of a hydrogen atom, was put it on a stamp, a New Zealand stamp. This notation is just an example of the notation that I showed you on the previous slide. Nitrogen and helium, which is the alpha particle, evolves to oxygen and hydrogen. And the New Zealanders were proud of the fact that the alchemists had discovered, or that Rutherford had solved the problem of ancient alchemists. But Rutherford wasn't happy to be called that, but that's the way it was viewed in the world. So this is a way to write in notation what happened when the helium, when the alpha particle, which is a helium nucleus, collided with the neutrons. Well, the last device to be discovered is the neutron, and in a very similar way, alpha particles from a source were shined on beryllium. The beryllium, in turn, this experiment, there was something going on in the region between the beryllium and, in this case, a paraffin screen, but it was very difficult to understand what was happening. However, people were able to see protons, they had now discovered, coming out of the paraffin. And Chadwick, the English physicist, determined that the particle that was emitted from beryllium when it was exposed to high flux of alpha particles were neutral particles, and he proposed that those were neutrons. And by a series of measurements and determinations, it was shown that these were particles, first of all, that were very massive, as the proton is. As the particles, they were not charged, as a neutron was expected to be. And these particles also had very little ionizing effect, because it takes charged particles to cause ionization of other particles. So Chadwick won the Nobel Prize for the discovery of neutrons. So, so we have the additional fact is that the neutron, being on charge and relatively massive, became another way in which one could explore and probe nuclei. Prior to this, I told you that beginning with Rutherford, people used high-intensity alpha emitters to bounce the alpha particles off nuclei, and by studying what happens to this bouncing off of nuclei, one began to get insight into the structure of the nuclei. The introduction of the neutron provided a second device for scattering off of particles. So by 1934, the basic structure of the atom was known. The core of the atom was a nucleus. The size of the atom is about 10,000 times the size of the nucleus. The particles making up the atom consisted of electrons outside the nucleus, and in the nucleus, protons and neutrons of sufficient number to make up the atomic weight and atomic number. The last point to make, and this is a point that is related to the issue of radioactivity, the nucleus can change into that of another element, either by natural radioactivity, as Becquerel observed in uranium. This is manifested by the spontaneous appearance of alpha, beta, or gamma radiations, or artificial nuclear reaction, such as that induced by the capture of an alpha particle or the absorption of a neutron. The discovery of the neutron led to a huge amount of investigation, and over a period of a year or two, virtually every element in the periodic table had neutrons scattering off the nuclei, and people had begun to systematize the response of elements of the periodic table to the absorption of neutrons as they scattered off the nucleus. And it was at this point that the studies that were done on uranium by Fermi, in which he scattered neutrons off the nucleus of uranium, that led to the discoveries that ultimately made possible the atom bomb. That's a very quick, perhaps too quick, description of how physicists got from the point where atoms were viewed as indivisible objects to they were viewed as objects, basically empty objects, in which negative and positive charges were mixed in such a way that the positive charges at the nucleus form elements that are responsive to the disturbances that occur when energetic particles from outside the atom collide with the nucleus. So I won't go on, it's the whole description, but that takes us to the point where we're almost where in 1939, people began thinking that it would be possible to build a bomb, but my time's up, so.
No, please go ahead and finish. I think we'd be very happy to hear how this relates to the.
Oh, okay, because what I wanted to say was that Fermi, as I said, shined neutrons on virtually the whole periodic table, and he found very quickly that he could systematize what happens. You can add a neutron, and nothing can happen except that the atom becomes a heavier version of itself. That's called an isotope. Or the neutron could enter the nucleus, and the nucleus could disintegrate into other elements that were identified as elements near to the element that was being exposed. And so this happened in a predictable way all the way up to uranium. At uranium, Fermi exposed uranium to energetic neutrons that struck the nucleus of the uranium, something happened because out of that interaction, material came out of that interaction that was itself radioactive, so that something had happened to the uranium nucleus. But because these new radioactive materials appeared, but no one could find out what happened. They went looking. The obvious thing they said was that it either became the next possible element in the periodic table, or it became something that was very close to uranium at some lower level in the periodic table. But you would expect that it would cluster around the location of uranium in the periodic table. No one could find it. And it took about a couple of years until Irene Curie and her husband discovered that if you looked at the detritus of the kind of matter that was present after shining neutrons on uranium, they found the presence of lanthanum. Lanthanum is another element in the periodic table that it's some 60 or almost 60 steps away from uranium, and but the question was, how can you get 60 steps away? I'm sorry, 35 steps distant from uranium in the periodic table. And other people read the result that Curie published, and they said, how can that be? But Otto Hahn and Fritz Strassmann, very good chemists, trusted Curie, and they went out to see if in fact they could repeat the result. And they too discovered barium, which would transmute to lanthanum by beta decay. That is to say, Hahn and Strassmann by chemistry discovered in the detritus of the neutron uranium collision an element that was 35 steps distant in the periodic table. Very puzzling. The chemists didn't trust their understanding of the nuclear physics well enough to make a conclusion themselves, and they asked Lisa Meitner, who is a physicist who was quite active amongst physicists in the nuclear physics community, if she could provide some kind of an explanation. Meitner looked at the problem, used a heuristic model of the nucleus called the liquid drop model, and basically said, yes, on the basis of the liquid drop model, one could imagine that when this neutron entered the nucleus of uranium, that it's like a water droplet. The droplet got bigger because the neutron had entered into it, and basically the droplet disintegrated in such a way that it simply split into two droplets. And the two droplets that it split into were this lanthanum that had been discovered by Curie, and another element that was similar in size, the lanthanum. And with the chemical detection of the lanthanum material, with a physics explanation of what had happened to the nucleus in order for lanthanum to be discovered, Hahn and Strassmann wrote a paper, which they published. That paper was read in late 1938, early 1939. And the minute it was read, the physicists who understood what was going on with nuclear physics recognized that the possibility of a bomb using the energy that was available in the nucleus was to be explored. So it was a direct consequence of people understanding the results of Fermi's experiment and finding sufficient evidence within science to proceed further. And the concept that people came up with, which is a concept called a chain reaction, And this is an illustration of a chain reaction. A neutron, if you can see on the left, a neutron enters a uranium atom, and that atom splits into reeded krypton and barium. And in addition to the krypton and barium, it emits 3 neutrons. So you get 3 neutrons and 2 new elements. The 3 neutrons themselves collide with 3 uranium atoms, which each of those split. And so you have a process where at each level of this interaction, more and more split uraniums are being produced. That's a chain reaction. The release of all this energy very quickly, typical time for a bomb to go from not being a bomb to having been exploded is about a microsecond. So that within a microsecond, suddenly you're releasing all the energy that's bound in a significant fraction of the uranium atoms that are in the bomb. So it's this phenomenon that is the core of the atom bomb that Oppenheimer and his crew were working on. So
Steve, that was an outstanding presentation. You took us through so many areas of science as well as history. And I'm really glad you spent that last few minutes with us to bring the topic to a conclusion. And I'll make one comment before we get to questions. I know this isn't the main part of your talk, but 2 things that will stay with me about this talk today are, one, the research you did on the electrometer. You saw a piece of equipment you hadn't seen before, and you did detailed research, and I think that was true throughout this talk. And the second was with Rutherford Stamp in New Zealand. I really admired that. It's great that people at that time in New Zealand appreciated science to that level. I think back, I don't know if America has ever appreciated science enough to put it on a stamp, but certainly it wouldn't happen in today's time. So that was a fun part of your talk. But with that, we've got a couple of questions so far. One live from the Friendly House. We're going to take that one first and go to Jeff at the Keystone Room in the Friendly House.
Yeah, thanks, Todd. Very nice presentation, Steve. A big part of this is detecting isotopes. So how did the discovery of detecting different isotopes go back then to determine isotopes from neutron bombardment?
I can't give you a general description of how isotopes were determined. I was more interested in, by the way, I didn't use the term isotope, I don't believe, in the talk. An isotope, with the nucleus, the type of element is determined by the number of protons in the nucleus. The weight of an element can differ. You can have many different numbers of neutrons in the nucleus, and so an isotope is an element that has the same atomic number as same number of protons as a number of other pieces, but weighs different than the other pieces. So an isotope is something that weighs differently. So all of us become isotopes every day when we eat lunch, but that's a different issue. But to answer your question, though, how are isotopes measured? I didn't explore that particular element of the exploration. I was very much interested, however, in how people determined that in the detritus of a scattering experiment, that there were barium atoms along with all the other stuff that would come out of the kind of barium experiment. And that was a nuclear chemist who would do that. And what I learned is, first of all, these elements, unexpected elements that showed up, were often radioactive. And so first of all, you could detect them with anything that would detect radioactivity, for example, a Geiger counter. Secondly, the chemists were able to take the the stuff that came out of the reaction. And actually, by chemical process, they were able to factor out of the stuff everything that was barium-like, things that would attach to one another like barium. And the ordinary expectation would be, like in the experiment that I described with Fermi, if they found barium, it was a mistake. Maybe it came from some impurity, whatever the case may be. And but barium didn't come from the reaction because that was not expected. So at some point in this process of chemically analyzing the outcome of the scattering experiment, the radioactive material that represented the outcome of the experiment would chemically separate itself from the barium and would show up to be what was more ordinarily expected, some nearby. The reason I'm pausing about isotopes, I could give one example of how isotopes were discovered. Uranium has three common isotopes. There are three isotopes you can separate from natural uranium. They were very much interested in the uranium isotope 235 and the uranium isotope 238. When they wanted to get samples of uranium of that size, it was very hard to find. I mean, it's not something that was commonly done in any kind of industrial chemistry. And they actually went to a physicist at the University of Minnesota who had a device called a mass spectrometer. And a mass spectrometer is a device that if you inject an ion of a material into it, there are electric and magnetic fields in the material that will bend the ionized material that you've placed into the mass spectrometer by an amount that's dictated by its mass, how heavy it is. Alnier, using a mass spectrometer, injected ionized material from uranium, and in uranium, more than 99% of the material is uranium-238. Maybe 0.5% is 235. So you're going to get huge amounts of 238, but the 238 being more massive won't bend as much as the 235, and you'll get the material enters the spectrometer, it's bent, it collides with a wall, with a pickup tape, and on the tape you'd have two separate elements where you'd find either the 238 or the 235. So that's one way that I know that people looked for, and particularly had to separate materials that had very large differences in their concentration. The mass spectrometer was an effective way to do it.
Let's go to a question from our Zoom audience from Al.
Yes, Steve. That very interesting story. I'm sure you left out a lot about, to get to the end time. I'm sure you left out a lot. There's one thing curious that you reminded me of when you got to Meitner and uranium in 1939, and that was that H.G. Wells wrote a sci-fi story about a uranium bomb in 1914. Now, I know that the periodic table goes back to the 1860s or so, and that must have had an awful lot to do with a lot of this progress, both the development of the periodic table and the understanding of the atom. Was there anything that he could have used to decide that uranium would produce this new kind of bomb?
Well, when Becquerel discovered natural radioactivity, he discovered it in uranium. And by 1914, people had good measures of how much energy was involved in the disintegration of the nucleus that gave rise to the alpha particles, beta particles, and what have you. So that I think any well-informed scientific observer would have known that uranium itself has some very peculiar properties, that there is a lot of energy involved in the uranium disintegration of the uranium nucleus, and I think an imaginative person might say, "Gee, wouldn't that make an interesting bomb?" So I think that's I don't know if it's true or not, but it's certainly a suggestive way that Lovecraft may have known that.
No, yeah, it was H.G. Wells, but
H.G.
yeah,
Wells up there.
he didn't get the microsecond right. His bomb burned, exploded continuously for a long time.
Yeah. Well, there was one of the problems that the group at Los Alamos were struggling with was, what if the bomb didn't blow up but simply fizzled, and that was a real concern. Not so much, well, of course, the failure of the bomb would be terrible, but the second thought was that if you did have a fizzle bomb, the enemy would have the leftovers of that bomb to learn about how to build a bomb themselves. So, but it turned out that was not a possibility. So.
The questions are rolling in. We'll stay in our Zoom audience for the next question and then take one from the friendly house. Let's go to Hank Robb with a question.
Hi, very fascinating. I am reminded by this talk that the physicists have solved the problem of how we can have death by explosion, while the chemists have solved the problem of how we can have death by poison. But we psychologists have failed to solve the problem of how we get death by short-sightedness. An unfortunate failure in problem solving. What I'm curious about is, when I took high school chemistry, which was the only chemistry I got a very nice periodic table that told me all about electrons and atoms. But that doesn't seem to be possible at the time that the periodic table was created in 1869. So what was that table based on, and how did they get it?
I'll give you my answer. I'm sure there are people who maybe know more about it than I do. I think Mendeleev, and there were other people involved in generating a periodic table. What they looked for were chemical similarities between the different elements that chemists had by that time come together, and so it was similarities of the chemistry of these different elements that allowed Mendeleev and others to organize, so that they knew at one point in the periodic table where element A is always superseded by element B and always followed by element C. And they would look at other parts of the table and say, well, here's another element A. This one looks like to that element A the way the previous one. So they use similarities in the chemistry of the materials to do that. The electrons, I believe they were the chemists had already devised concepts of valence. That is, some things are more chemically active than others, and they would talk about the valence of the element in a certain circumstance as being a measure of its chemical activity. And so they did infer to the existence of something in the atom which differed by this valence number, and attach the concept of electrons to that concept. So they didn't get into inside the atom, so to speak, to look at the thing itself, but rather they looked at the atom in light of its behavior and all the other atoms around it, and used that as the ordering principle. Of course, they were very good at it too. I mean, I have to say that when I commented earlier about how they detected the materials out of the uranium neutron scattering that led them to understand that fission had occurred, they were working with large chunks of matter, gram-sized chunks of matter, and they were able to detect the presence of maybe 2,000 or 3,000 atoms of a particular radioactive substance in the presence of 10 to the 23rd other atoms. Now, I have to say that I was very impressed when I read that, and I'm impressed when I repeat that about how clever chemists are and were in their ability to separate different things from one another using chemical means and mechanical means and whatever there is. But the history of the periodic table is worth studying on its own too. And I'm sorry I can't give you a better answer than I gave you.
Well, thank you so very much.
Let's go to a second question from the friendly house.
Hi, I had a question around in the movie Oppenheimer. One of the kind of dilemmas that's brought up is the idea at like different levels, people came to be concerned that this chain reaction of could continue in an uncontrolled manner, in a sense where they weren't sure when they tested the bomb even that it wasn't going to just keep chain reacting until it like destroyed a part of the atmosphere or something like that. I was curious, is there what was that kind of a big discussion in terms of like the science? Like, is that historical? What kind of information do you have on that? That is a concern that came up in the discussions in 1942. Edward Teller was the one who raised the issue about the possibility of the atomic explosion, if you like, igniting by causing a disintegration of the nuclei of elements that were not involved in the bomb, that were part of the environment in which the bomb was going off. And that discussion caused enough concern. The story is that Oppenheimer went to speak to Hans Bethe, who is another physicist who was very knowledgeable in the relationship between elements in what he was studying were elements in stars, but elements that share the same environment, and how they can impact one another in various kinds of activity. And Beda's read what Teller had said, and what I read is that his response was, "Don't worry about it. You know, it's not going to happen. And that's not going to be an issue." But it wasn't an issue that came up. I know in the movie, I believe there's a scene where Groves asks Oppenheimer about the problem, and Oppenheimer says, "No, we're 99% sure it's not going to happen." And Groves, gives him the fisheye and says, that other 1% worries me. And but I think the physicists believed that was not possible. And I think, by the way, I think the way that they approached that is to approach this problem of the detonation of a bomb with the recognition that within a microsecond, the bomb itself, the thing that was built to be a bomb, has expanded so much that the neutrons required to enter the nuclei and continue the chain reaction simply can't get there. The thing has become too big to support a chain reaction. And I think that's the argument that people used, that wasn't going to happen in the atmosphere. But again, thank you.
Yeah.
We're getting close to our 11:30 stop time, but I want to honor all our questioners. So we'll wrap up our Q&A this morning with a question from Renga.
Thank you very much for a very nice summary in a very short time. But I thought there is another point which may like to elaborate a little bit more, namely that for example, uranium-238 is not the one which fissions, but uranium-235 is much more fissionable. That is the idea of the so-called cross-section, namely that which particle with what target can create the reactions, how fast it can go. So that was a very important one, because the U-35, which is a very small percentage of the total uranium content, has to be separated out by an elaborate process of mass spectrometry and other things. And that was one of the important things. So you may like to say something about that.
Yeah, I appreciate your question. The whole discussion of this thing called cross-section, and it involves separating out the effects of U-238, U-235. The discovery was that U-238 could not participate in the bomb process, so that U-238 became a burden. They had to separate it and get rid of it. And U-235 was the only device that was the only isotope that could participate of uranium in the bomb. What I was going to say is that the difficulty with U-238 is that it would absorb neutrons without producing new neutrons to maintain the chain reaction. Its cross-section for that process was simply not big enough. That's a superficial answer. I would like to go in and talk about that at some length, but it was one of those things that I had to discard as making my way through the world here. But you're right. I mean, the separation of U-235 from U-238 was a several billion-dollar 1944 process. It was a huge expense. It was absolutely essential, though, for the production of the bomb. Interestingly enough, the other element that was used in the bombs was plutonium, and ultimately plutonium was the element of choice for a bomb development for a lot of reasons. And it's probably fair to say that if there are atom bombs out there these days, there are no doubt plutonium bombs.
Thank you so much, Dr. Kral, for a very informative, spirited presentation and an excellent Q&A.